Okay, as I was saying in the previous video, this is the electromagnetic spectrum. This full array of wavelengths is emitted, for example, by the sun. Most emitters on Earth will not emit this entire range. It will emit a very small part of this range. This is showing us from very large wavelengths. You can see these are meters and kilometers long, but have a very low frequency, all the way down to very small wavelengths. This is on the order of the size of a nucleus of an atom, and therefore has a much higher frequency. And that relationship comes from the fact that the speed of the wave is equal to the wavelength times the frequency. So if the speed of the wave is constant, which it is, then as I increase the frequency, the wavelength has to get smaller. This section right here, this tiny little sliver out of the electromagnetic spectrum that we refer to as visible light, we have a tendency to think of that as very special. And I want to emphasize, it's not that these wavelengths are different from the others, it's that our eyes are specially adapted to be able to interact with these wavelengths. So visible light is special only in that we can't see the other wavelengths. Otherwise, the physics of how these waves behave, the red electromagnetic waves, the green electromagnetic waves, compared to X-rays and radio waves, the physics of it is all the exact same, just a difference in wavelength and frequency. So again, the key is to know that all of the explanations and equations that we're going through apply just as much to red light as they do to blue light, with that variation then in the wavelength and frequency. This is a little animation clip that I pulled out of a video that I have shared under modules. It's the Veritasium wave interference video. I'll actually reference it again in a little bit. It is here to remind you from Physics 140 mechanics that electromagnetic waves, like other types of waves, like water waves, display interference patterns, including destructive and constructive interference. This pattern is that there are two sets of waves being created by the two different tennis balls bobbing in the water, and as the waves overlap, the wave formed down here from one overlaps with the other, and it sends out these patterns where it is sometimes the two waves are adding together because they are crest to crest at the exact same time, and other times right here you can see that line where it is the crest of one and the trough of the other. They're adding together to make zero, a large top of the wave and the bottom of the other wave in the same place at the same time, therefore adding up to be zero. And again, if you don't remember that from Physics 140, then you may want to take a look at that chapter. The big concept I want to get to right here, we're building up to a famous experiment for how we know that light is a wave, but really one of the starting points for it is this. All waves, when they pass through an opening, are able to bend somewhat around the edges of the opening. Waves diffract or spread out. And this is more obvious when the size of the opening is about on the scale of the wavelength. It's going to happen also with larger openings, but that's the size that really is where it's most obvious. This is a well-known wave behavior for things like ocean waves and breakwalls at a harbor. It was observed with light hundreds of years ago, and it sort of set up the question that, does that mean light is a wave? And if so, what is it waving in? Light does this, and if you pass light through, for example, a very small aperture like this, a small round hole, you would get an interference pattern that looks like the one you see here. That's not usually what we talk about, though. Usually what we talk about is something more like this. This is what happens if you send light through a very narrow but tall opening. We usually refer to it as the slit interference or double slit interference patterns. This pattern here is what you would see if there was a single slit of interference pattern. In other words, light doing this. Light waves passing through a small opening about the same wavelength, the same size as the wavelength. So for visible light, let me back up just a second here. For visible light, we're talking about the slit has to be somewhere between about 400 and about 750 nanometers. So we're talking about a very small opening. If light passes through a hole about that size, you get a pattern like this. If light passes through a single slit that size, you get a pattern like this. And the fact that it's bright in the middle is not what's weird. What's weird is that over here there's a dark spot, and then another bright spot, and then a dark spot. This is what it actually looks like, this part down here. This up here is a graph of the light intensity, where it is most intense right in the middle, and you can see it drops off to being not intense, but then there's these little bumps out here of light intensity. So what we're talking about is this. The double slit pattern is really what we want to talk about. It emphasizes this a little bit better, so it's the part that you're most likely to see. If you shine light here into a barrier, and this barrier has two slits, and these slits are kind of exaggerated in this drawing. They're supposed to be on the scale of 500 nanometers or so. The light patterns that come out the other side here, they're projected onto some sort of screen, a projector screen. So we'll repeatedly refer to a screen in these experiments, and that's what we mean, like just a sheet that the light is passing onto. And it gives an appearance like this. This is what you would see if you were doing this experiment. We talk about bright fringes and dark fringes, and we denote the bright fringes with this lowercase m, which must be an integer. We're usually not very concerned about the centerpiece, but we're talking about the bright fringe that the first one out, the second one out. And we don't usually care about the difference between the first one on the left and the first one on the right, because the math is the exact same. It'll be symmetrical. As long as this barrier and this sheet are parallel to each other and not set off at angles, which they're not. The dark fringes, we don't usually spend time talking about the dark fringes other than to know that they are exactly in between the bright fringes. So here is the big picture of what is happening to cause this pattern. This is sort of an overhead view. If you do the experiment, you get this pattern, but horizontally, sideways, assuming that you have a setup like this. So that pattern here we're showing actually looks like this here over on the right. This is the pattern, this is how it forms. So you have these wavefront, these rays over here, these waves coming in this way. And when these waves get to this barrier and pass through slit 1 and slit 2, they are usually, the distance between them is usually somewhere on the scale of how big the slits themselves are. So again, on the size of the wavelength. The light coming out the other side will be acting like 2-point sources, 2 individual sources. So the pattern of this slit, the waves coming through, should be as though this was the actual source. And the pattern coming through on this side should be as though this is the actual source. So what we should expect is this pattern, which is what we saw in the Veritasium video where he's bobbing the 2 tennis balls. He's making this pattern in the water. We're getting that from a single light source by passing that single light source through this barrier, these 2 slits. And on the other side, you get this pattern on the screen over here where there's a maximum and then a minimum and then a maximum and a minimum. The maximum is the bright spot. The minimum is the dark spot. Maximum, minimum, maximum, minimum. I guess the pointer doesn't show up for you guys, does it? Does it show up as a big yellow dot? So it's not a very good pointer then. Again, this is the view from above. This is what it looks like. So here's what happens. From a more mathematical approach, I want you to assume that the words across the top here, the double slit interference, assume that right across where those words are, that's the screen that we're projecting onto. And you can see at the bottom down here, this is the one opening, and this is the other opening. And they're a distance d apart from each other. And this is a lowercase delta, which looks a lot like a d, and that's unfortunate. I'm not getting into the angle so much here. But what I want to point out is what's happening is that directly across from this distance d, centered on it, directly across, following this dotted line, we would have a point where the waves coming through the right slit and the waves coming through on the left slit, they're coming through in step with each other because they're actually coming from the same source. So they come through as two what we call coherent sources. All that means is, like the video where he's bobbing the two tennis balls, he's bobbing them in time. He's not doing this. He's having them actually hit at the same time. That's modeling what's happening here as these waves come through, and the waves coming through the right slit, the waves coming through the left slit will reach here at the exact same time, perfectly in step with each other. They will have a constructive interference with each other, and you'll get a bright spot. As you move a little bit farther out, once you get over here somewhere, you'll have a place where the waves are no longer adding to each other. They're destructively interfering. And the reason for that is what this drawing is trying to show. The path that is being taken by this pink semicircle of a wave, the path that it's taking to get to this point is longer than the path the blue wave takes to get from this other opening to that same point. This point right here is a different distance from this opening than it is from this opening. That's not surprising, but what we need to think about is if the waves are coming through in step, what does it mean when they get to right here? If these two waves, the blue one and the pink one, coming through this opening and this opening, reach here and they are both peaking, both cresting at the exact same time, then you get a constructive interference. But at some locations, one of these waves will be cresting while the other is at a minimum, at a trough. And so you would have the one maximum plus the one minimum added together, and they give you, therefore, nothing. They destructively interfere. So that's what we're getting at here, is that along this wall, you have this trigonometry down here. Again, is just to show how it works, how it builds up. That's not the equation we're going to use. Let's see if this is. This is. On this screen over here, you have m is the integer 1 or 2 or 3. The wavelength is part of the calculation also. D, which is this distance here, and sine theta, we're actually probably going to look at another way to write this, but sine theta is, the theta is measured from right here to wherever the point is on the wall, on the screen, over here. So let's say we're talking about this point on the screen, not the center, but as we move farther out, we move out to here. This point on the screen is some angle theta away from where these two slits are. This equation is the relationship between how big the wavelength is. Did you mean the first bright spot or the second or the third? D, which is how far apart the two slits are, and sine theta, where theta is just how far out you're turning. What we'll see is that sine theta actually is taking into account how far do you mean here and how far do you mean here. Since theta is this angle on a triangle I'm making like this, I'm tracing it out right here. This is my hypotenuse of theta, this is my adjacent of theta, and this is my opposite of theta. How far away the screen is from the slits is this adjacent side. And it's also this hypotenuse. As the screen gets farther and farther away, the hypotenuse and the adjacent will both get bigger. And because they do, then the opposite side does also. So this trigonometry here is telling us that if, let me back up real quick. If you were doing this experiment, oops, I went too far. I'm so sorry. If you were doing this experiment, then having this screen really close to the apertures here, you would get that same pattern, but pressed together. And as you move the screen farther back, it gets spread out more. This is not news to you if you've ever done something like shine a flashlight at a wall. As you get closer to the wall and farther away from the wall, you see that farther away, the flashlight pattern gets bigger and bigger and bigger, but it's the same pattern, just bigger. So I'd like to demonstrate a little bit. This is a video that I took from the Twitter feed of a physics teacher. They're just trying to demonstrate here something visibly. These two paper clips over on the left represent the two slits, the two openings, and as the two openings have light waves passing through them, you can see at different points along this line here represents the screen, sometimes this wave and this wave reach here exactly in step, because the distance that the one travels is more than the distance the other travels by exactly an integer number of wavelengths. If this one is longer by exactly one wavelength, then they reach that point perfectly in step. If it's by exactly 2 wavelengths, then they reach exactly in step. There they are out of step, there they are in step. Where they're in step gives us the maximum, the bright spot on the wall. This is what it looks like if you actually do a lab with a laser passing through these openings. If there were more than 2 slits, you could get a very similar effect, but it actually cleans up a lot the more slits you have. And while we're not going to do the math of that, I do want to show it to you, because if you wind up with like hundreds or thousands of lines, you get something called a diffraction pattern. And it looks like this. This is what happens if you shine a green laser, and that's just a green laser pointer, through a diffraction grating. It gives you that wonderful effect. And that effect depends on how far away the grating is from the wall. It also depends on the wavelength. So as you can see here, red wavelengths, being bigger wavelengths, have a more spread out effect than green, which is a bigger wavelength than violet. The violet ones are the most, it's the same general pattern, but it's more compressed for the smaller wavelength violet light. And that's what it looks like. So again, the effect depends on the spacing of the slits from each other, or how small the grating is, and the diffraction pattern also depends on the wavelength, though. That's what we're trying to emphasize here. We'll actually come back and do the calculations of this when we do chapter 27. Right now I just wanted to sort of lay the groundwork for it, and we are going to instead, for our next video, get into mirrors and lenses.